Welcome to the Laser 15 for the first time in Concordia. This is a joint effort between Concordia, the Leonardo organization, and thanks for a lot of people that has been working so we can make this happen. Nina Czegledy, we are co-curating this activity, thanks to Gabriel and Marcelo, and a lot of people, Molte from the technical side, and Milieu, Le Parc, Hexagram. So we are happy that also we are receiving here a lot of people today. Thank you for coming, and I'm going to pass this to Nina Czegledy.
Hello, everybody. My name is Nina Czegledy, and I have been with the Leonardo and the Laser organizations for a long time. The Laser organization is now celebrating around the world in more than 50 locations on all 5 continents. I would like to thank you very much, Ricardo, the co-chair of this event, and also my close partner in all sorts of mischief around the world for several years.
So I forgot to say, just my name is Ricardo Farra. I'm professor here at Concordia University at the music department. Okay, I'm going to introduce our guest of today. So the first presenter is Marcelo Wanderley. So Marcelo has a PhD in acoustics, signal processing, and computer science applied to music. His interdisciplinary research focuses on the development of novel interfaces for music performance. He has authored and co-authored numerous publications on new interfaces for musical expressions, including the co-edited volume Trends in Gestural Control of Music and the textbook New Digital Music Instrument. I need to mention also that these are like really new. It's a new field that really Marcelo has been helping to develop, not just here, but in many places. He's the director of the Input Devices and Music International Interaction, not international yet, laboratory at McGill University. And as far as we talked before, you are also the director of CIRMMT, right? Perfect, okay. And Gabriel Vigliensoni is assistant professor in creative artificial intelligences, design and computational arts here at Concordia University. His work currently explores the creative affordances of the machine learning paradigm in the context of sound and music making. His practice merged formal musical training with extensive studies and experience in sound recording, music production, music information retrieval, human-computer interaction, and machine learning to explore and develop novel approaches to music composition and performance. So we'll start with Marcelo.
Je ne sais pas quelle langue parler, alors je commence en français parce que quand même on est au Québec. Et les gens parfois ne savent pas qu'on parle beaucoup de français à Concordia et à McGill. On n'a pas forcément unilingue. Alors merci d'être là. So now I switch to English. So I'm Marcelo Wanderley. And I'm at McGill, as Ricardo said, at this lab and at CIRMMT. That's a kind of hexagram, but more for music and technology and science. So first, thank you, Nina and Ricardo, for organizing this, and thank you for being here. So I'm trying to speak a bit about a big thing that interests me is interaction. So interaction, which kind of interaction? So human-machine, human-computer, etc., but of course in the musical context. So what does it mean to interact with a computer to generate sounds, create sounds, transform sounds, whatever? And I'll be showing some examples of this research, some old ones, some newer ones, but always around this notion of interacting with a device to create sounds. Ooh, it buzzes. Ooh. So why interaction? So that's me actually long ago, because I'm not a musician. I'm a professor of music at McGill, but my background is electrical engineering. So one of the key words there is I have to collaborate. And I have to collaborate, obviously, with high-level musicians, performers, composers, etc., etc. So what I try to do is bring this more engineering knowledge and some scientific knowledge into this question of interaction in music. So what can I learn from acoustic instruments high-level performances, what can I bring these to new digital musical instruments, instruments where the computer actually is part of the instrument. A computer can be, these guys can be, a watch can be anything these days, right? So how do I interact with this technology? How do I play the computer? And two main research interests, so creating digital musical instruments where the computer plays the sounds and I connect some sort of action or gesture or interface to the computer, but also this question of analysis of performance. So looking at motion capture, for instance, of performers playing instruments and then comparing styles. So I'll show a bit of a few examples of each of these. And as Ricardo said, I'm back to directing CIRMMT. So CIRMMT is the Center for Interdisciplinary Research in Music, Media, and Technology. And actually, I was a director from 2011 to 14, and I said, never again. And then, again, never say never, because, and since July, I'm back to the future with the same thing. So, why music? I don't think I need this slide for you, but it's a slide I always place, because sometimes it's not obvious why music and not satellite communication, right? Well, because it involves a lot of people. In Canada, I think 35,000 people identify as musicians and singers, 4,200 conductors, composers, arrangers, etc., etc. It's a huge business. I think in 2020, it was more than $500 million in streaming and digital music revenue, so it's not negligible. And that's Canada, right? If you look in the US and et cetera, it's way bigger. Impacts a lot of people. So 93% of Canadians reported listening to music, 96% of millennials. And actually, how they listen to music, well, millennials, 79% reported listening through some sort of digital device, or their phones, or something like that. So knowing that phones are not made to play music, right, typically, what is the impact of technology on the way we perceive music, in the way we enjoy music? I mean, it's not transparent. Technology is never transparent, right? We need to be aware that the choices we make or the devices we use, etc., they will have some sort of effect. And so understanding the role of technology in musical production, performance, etc., is critical. So, music and digital technology. So, computers making music, when did this start? Right? There's some experiments, I think, in Australia already in the late 40s. Very basic, right? I mean, they're not. But basically in the 50s, already, it's very early in computing. I mean, digital computing, 50s is really early, right? But already people were using computers for either composition, right, computer-aided composition, or eventually sound synthesis, late 50s. So it's actually not from yesterday. It's like several decades people are using. And actually, digital technology has a tremendous impact in everything. It's hard to separate something that today doesn't imply or at least relate to digital technology. In this case, also, it's interesting that digital technologies allow for new musical types of music, right? And types of sounds, et cetera, et cetera. And here's an example. So that is an excerpt of Christian Bouchard's piece, Angle Mort. And again, you know, try to do this with acoustic instruments possible, but maybe not so easy. So again, what's the impact of technology, for instance, in this kind of output? This is not as advanced, the next one. So actually amazing piece, right? Thank you. And actually, just it's a joke because actually I'm pressing one key, right, one note in the Arturia kind of demo thing and a sequencer. So I go the sequencer on the CP80 or the whatever, and I'm just putting on top of each other. So I mean, looks like I know what I'm doing. Right, so again, and this is because of digital technology, right? I mean, I don't think it's better or it's, but it allows different access to music. So acoustic instruments, and you have a clarinet. Where is the interaction? Where is the sound generation? Both are in the same place. You can separate. You can tell the reed is where I interact and the sound comes from. Right? I mean, there are the keys there, etc. You can talk about radiation, but basically everything happens at the same place. With digital instruments, the interaction happens somewhere, so the interface. In this case, that's the T-stick that some of you might know, because it's very old. And we still keep doing them. So it's one that has some history of performance too. But the sound generation typically happens elsewhere. And this elsewhere might even be a microcomputer inside the interface. But it's not the same element that does sense the gestures and actions and generates the sounds. So you have to kind of find a correspondence, find some way to associate these gestures and actions to the sounds. So how to play this? How do I play a stick like that? Is there a natural way to do it? There's no physics anymore in the sense of vibrating a string of a certain length with a certain material gives you a certain pitch. So it's a very simple old model of a digital musical instrument. You have here the device, let's say the tube. You have here your computer, let's say your watch these days. You have to find a way to capture the gestures that a person will do with the tube. And that will be through sensors here. And then this digital data typically will be connected to whatever synthesis algorithm you're going to use. So amplitudes or partials or physical models, et cetera, et cetera. And then you can have feedback, et cetera. This is very simple because it's a unidirectional diagram, doesn't take into account couplings, doesn't take into account necessarily connections between actions, et cetera. But represents pretty well when you use MIDI, for instance, and sensors and a controller, that fits. One of the important things, and why do I put these references here? Because mapping is one of the places that actually has been used as a case study for AI in machine learning, right? For instance, the Wakinator that I guess Gabriel will mention, and others before even the Wakinator, etc. So this is one of the points where machine learning and artificial intelligence can be very useful. Because again, there is no natural way why certain gesture would create a certain sound. There is no necessarily natural response, right? Then there's the question of learning. You might make something that doesn't look really natural, but then you might learn how to play this and develop something else. So why then human-computer interaction in music? So what is similar when you talk human-computer interaction? You think about tablets, you think about phones, you think about computers, right? But in this case, it's to generate sound. So actually, in this case, it's not a one parameter with a one action doing a one command there. Many parameters are simultaneously controlled. The control mechanism is typically physical and multi-parametric. You don't do one thing at a time. There is no set of options. There is no menu saying choose from these items here. You can control any parameter at the same time. Series of discrete and control signals. Overall control is the main goal. You don't necessarily issue commands. This is very important, right? So the notion of ambiguity is not necessarily a problem in interaction in music. So if you do a gesture on a tablet and the tablet misinterprets the gesture, you might be in trouble. But in a musical instrument, the musical instrument don't necessarily understand your gesture. You use these as streams of data, right? So it's very different actually. Even if you use the same device and if you use similar software, the results and the way you use is very different. There's an instant response and you experience a moment-by-moment state of the instrument. And the practice, the notion of practice, right? Hello? Oh, thank you for it. Right? So what are the implications? There is no easy definable task. What is good music? What is a good performance? You know, there is no variable to say this is good, this is not as good. It's not like sports, the fastest you run or whatever. Time is extremely important, right? Gesture capture, low latency, high resolution, repeatability, etc. Gesture is typically treated as a streams of data. That's not necessarily always the case, but you don't necessarily need segmentation, recognition, identification, right? So again, ambiguity actually can be a plus. And practice and continuous learning. So this we have to take into account when we design these instruments. These are pretty much very important requirements for the design. Two-handed, haha, right? Typically, you don't use only your preferred hand. So, examples. This is a bicycle wheel, right? So what do you do with a bicycle wheel in Montreal in the winter? If you don't have special tires, it can be pretty nice to do a musical instrument. And this is 2005 called the gyro tire. So it was Elliot Sr. who built this as part of his master's thesis. How do you play it? Again, there's no reason why this should be the outcome of his movements. It could be this. Or it could be a sequencing, right? I mean, depends. Every time it turns on the same position, you get a beat, etc., etc. So again, it shows that there is no natural. It's not necessarily better or worse or whatever. It's lots of aesthetics and choices, etc. So this I will skip. So let's see some examples where I do. So first I start with something about motion capture performance. So understanding very specific gestures in highly skilled performance. Can I use then some of this information to design my new computer instruments? The second is, okay, suppose I want to look what happens if musicians play an instrument inside an MRI. Anybody has been on an MRI machine? Right? It's not really a stage condition, right, for a musician. So what does it imply when you design an instrument that you want to be played so that you can measure whatever is going on the brain of the performer? Can you just take your instrument if it's small enough to fit into the room, etc.? So lots of engineering questions there. And the last is a project for beginners. So you want to build an instrument, but you're not necessarily super skilled in engineering, but you have this idea, well, can I have systems that help you get something immediately out of this idea? So let's get a violin, and we want to understand what's going on exactly, the interaction between the string and the bow. So this was a project in 2007, 2008 with a visiting researcher. And the idea is we put a bunch of markers. So these markers, that's passive infrared motion capture. So the cameras will see these points and will pretty much filter out everything else. And then you can track the points with multiple cameras and create a model. You do the same with the bow. But you also need to measure the pressure, right? The force the hair is applying to the string. So in this case, we use sensors, strain gauges, etc. to cover. You can do this with markers too in different conditions. So we get a performer that's Lambert playing violin. You see that already it's not necessarily the best conditions for a performer. There's a bit of cable here, there's et cetera, so you're not on the most ecological. But you can get this kind of result. So the obvious one is reconstructing. etc., right? But the most interesting in our case here for us was to look exactly what's happening at the intersection between the string and the bow. So here you see the bow and the strings, the angle of the bow. Here you see each of the strings, the force, and this is a diagram between the velocity and the inclination. And now let's hear the song again, but looking as almost like a microscope to see exactly what's happening there. So again, this allows you to see as if you have the microscope to look at exactly the detail you want. So what applications? Well, we could compare beginners with experts. We could compare different performers with different interpretations of the piece, et cetera, et cetera, et cetera. So another application of AI that's happening more and more these days is you can use, one of the problems with motion capture is putting the markers, looking for missing markers on the cameras, et cetera, correcting mistakes. So all of these can benefit from more automated processes, so that then you can have less time to set up these measurements and have more people and actually have this as a practical training or practical tool instead of just a lab. We are still not there, but it's becoming much easier. Right? And also the interpretation of data, so looking at style, etc. So this was one. And it's really acoustic instruments trying to understand what's going on at this level of detail. So there's something about motion capture if you're interested on the Oxford Music Performance Handbook. More the technical level. So now, suppose I need to understand what's going on the brain of, on the head of the performer into the MRI. Of course, this is a collaboration, again, the interdisciplinarity, right? So it's with researchers Robert Sartori and Virginia Penhune, and also Melanie Segado, that I forgot to put, but she will appear on the video. And actually, this was a master's and then PhD of a student in my lab, who's in electrical engineering, Avram, who actually designed first a keyboard type of controller, then a cello, right? So first, the cello doesn't fit really on the scanner, right? I mean, you can't really take. And there's a lot of problems, actually. Well, if you know how it works, it's basically a huge magnet. You cannot take metals, and some sort of metals mostly, into the scanner, otherwise it can be catastrophic, literally lethal. Can get someone seriously hurt or worse, right? Then the instrument cannot impact the measurement, right? I mean, if you do something and then there's noise on the measurement, then you don't get much further. And of course, reliability, et cetera, et cetera. So these are really big constraints. Good to know, right? So these are our major constraints. It's a very different type of design. And I will show a bit of this video here. There's a 5-minute kind of short video talking about the project. And just to have an idea, well, first, what the scanner looks like and what the cello looks like. Cello. So it's not really a cello.
The basic idea behind what we're trying to do is to use music in a global way to understand brain function.
I look at what happens in the brain when cello players are playing the cello, which is exciting to me because I am a cello player and a neuroscientist. Playing the cello inside of the MRI is definitely very different than playing the cello outside of the MRI. For starters, you have to be lying down, which is a non-standard position for a cellist to be in. There are also the constraints inherent in the instrument itself, being that it doesn't actually have a resonant body, so you don't get the vibration feedback that you're used to getting from your instrument. It's also equipped with gut strings, which are a very different feeling than the metal strings. They're much harder to get sound out of.
So in this experiment, for the first time, we're looking at how the brain of a highly trained musician, specifically a cellist, is working when they're playing their instrument. So this has never been done before. The reason we do that is because music engages most of the most complex aspects of human cognition. So it involves hearing and listening, it involves motor actions to produce sounds, it involves memory, it involves emotion, it involves attention, it involves learning. So something like playing a musical instrument is a remarkable achievement that humans have.
So if you're interested, there are some publications on this. But again, this is the important thing about multidisciplinary or interdisciplinary collaboration. This wouldn't be done in music technology alone. It wouldn't be done at the MNI, the Montreal Neurologic alone. So you need this kind of resources like CIRMMT or Hexagram, etc., where this kind of research can happen together at the same level where the technology and the science happens in true collaboration. The last one is Probasio. Probasio was a project, again, for beginners. So very different application. Now you want to build an instrument and you want to find ideas. Well, I don't really know, how can I get inspiration? And then if I find something I want to do, how do I build this instrument? So functional prototypes is the idea there. It's a collaboration with Felipe Carigario, who was doing a PhD at the time and is a professor now in Universidade de Pernambuco in Brazil. And so the first part is to find the types of gestures and actions you want to do. So I want to hold it this way, or I want to play as a cajon there, or I want to hold as a wind instrument, name it, right? The second is the type of actions you want to do. So actually I want to have something that I turn, or strings, style, or slides, etc., etc. So from this, you can choose the kinds of controls and instruments you do. So for instance, if you want this posture with these two controls, you get this guy. If you want that posture, etc., you get that guy, right? So the first part is just proposing ideas. Again, we are talking beginners, right? We're not talking really designers or musicians who know what they want. But it's an experimental tool. But then, once you get to this part, the cool thing is that you can then have your controller built by yourself immediately. So you choose this control. Once you connect, it has already a sound associated, and you can immediately test and say, oh, that's what I want. No, that's not. And you can, it's a kind of almost like a Lego thing that you start connecting, but all the technology issues are hidden from the performer. Right? I mean, designer. You can connect multiple basses, etc., and it always ends up as a guitar, right? So it would be a guitar style something. And then, but you see that again, everything is kind of transparent. You put it, it works. You take it out, it disappears. And now the guitar. Etc. Right? So these are just very short examples, but it shows again that you can go in so many different directions for experts, for beginners, understanding performance, etc. And I want to end with this. It's a blog, whatever, at Le Monde. There was an interview about interdisciplinarity and music. This is 2016 or 17, right? But there, I think there was an interesting discussion. It's a kind of a joke sometimes, but I've seen this happen over and over, and I want to hear your opinion about this. Is this graph that I like a lot? And my impression on this interdisciplinarity is actually there's a lot of conflict. And actually conflict is very good, actually, to get people to agree on something and eventually bypass this initial ideas they had into something
So good evening, everyone. Thank you very much for being here on a February evening. Thank you very much, Nina, for the invitation. Thank you very much, Ricardo, for the invitation. And I'm very pleased to somehow sharing a panel with Marcelo. Marcelo was my supervisor during my master's, so it's really an honor being here. The invitation that Ricardo and Nina made was somehow to talk about data and interaction in the context of machine learning. And I would like to somehow share with you how I integrate these techniques and these approaches into my creative practice with sound and music. So I will present in this talk my research on modeling musical patterns with small and custom bespoke data sets and exploring the control and steerability of neural audio synthesis models through data and interaction-driven approaches. So I will begin with a kind of a brief critique of the limitations of the so-called foundation models in expressing musical intentions and agency. And I will highlight also how small data sets can give performers, as musicians, a greater creative control when using machine learning models. So, and finally, the idea is that I will illustrate some of these ideas with examples from my own creative practice with sound and music, and showing how these approaches can support a rich, sustained musical practice over time. So that's the overall gist of the presentation. So I would say that current popular and media discourse around machine learning, artificial intelligence, AI, often, particularly in sound and music, often fixates on one particular form of contemporary AI, which is a large general purpose generative model trained on a giant data set, which is capable of outputting a audio signal that mimics a relatively wide variety of usually Western popular music style, often in response to a short text prompt. So this is our interaction. We type something, and then we wait. We type and wait. So that's very unmusical for me. I mean, sometimes you can do this kind of thing, but there is something missing there from my perspective. And this approach is based on the assumption that these models are useful, perhaps not for musicians, but for lay people, people in the street, any person in the street. So, okay? And also that this utility outweighs the many drawbacks of this approach, all the legal, ethical, and environmental issues of this, on top of all the musical and artistical challenges that comes with all these models. But finally, the reality of sound and music making in sustained or for sustained musical practice is very different, because a text prompt gives musicians a limited ability to express their intentions and communicate an idea. So there is something more than this gesture only, I think. So I propose that we should consider alternative approaches to communicate intention when using machine learning or AI. And the first one is that I think that we can use data, the data itself, as a vehicle to communicate our ideas. And we shall explore other modes of interaction with machine learning models to capture this intention and our creative agency. So one of the core ideas of this is that instead of just considering data as a representation of so-called ground truth, we can think of training data as the vehicle or one of the vehicles to communicate our intention. So if the data sets that we use are somehow small, we can curate most of the data points that are present in the data, so that we can use also the training step of the model as a place where we can embed our creative agency. And also in terms of embodiment and steerability, we can employ other modes of interaction to capture our intention and our agency. And I believe that the embodiment of a musical system is important because we can map our human gesture into some sort of sonic output of the system. It's important, the relation between our gesture and what it's being produced by the instrument, I think. For example, if you have a violin, you expect a specific sound of the violin. If you have a synthesizer with a predefined set of sonic output, you expect that specific sonic output. So the idea here is that if we can map the human performance space, our space, the space that we know, into the high dimensional latent space of the computer, we can enhance and we can improve the expressivity, and we can also introduce what I say it's the long-term coherence, which is often lost in state-of-the-art generative models. And I will touch on that point again, the long-term coherence, the narrative. So in my creative practice with music and machine learning, I'm interested in two things, basically. First, machine learning systems that can be trained on small data sets so that I'm in control of the data set. And the second thing is machine learning systems that can be steered and controlled in real time. So I want to be part of the process of guiding the machine towards a certain direction. So for the first, I would like to share with you a research project on the modeling of rhythms with machine learning, and actually for the generation of the drum patterns. And in this project, I will demonstrate how useful models can be learned from very small data sets, like a dozen of examples, and how modifying a data structure of a network and can alleviate some of the biases that towards certain type of users and certain types of music. So this project started by the idea of that I wanted to model rhythms of some contemporary music genres, such as footwork from Chicago, two-steps, dubstep, and drum and bass from the UK, trap, dembow, and kwomp from South Africa. And these rhythms interest me because they exhibit the so-called tempo octaves, so that we can dance to a specific tempo, or we can dance to half or double. For example, you can dance to dubstep, or people can dance to dubstep at the archetypical tempo of 140 BPM, but you can go half of that, 70. But also because these rhythms exhibit lots of triplets. So instead of counting something in 2, you can also count in 3. And that's pretty common in many rhythms, not only from these contemporary music genres, but also in rhythms which are traditional in Latin America. For example, all those emiolar type, pam, pu, pa, pum, pa, ku, ka, ku, 1, 2, 3, 1, 2, 3, 1, 2. So all those type of things, you know. And in some cases, that mix of 2 against 3 is so strong that it's an intrinsic part. It's a stylistic signature. For example, in this example comes from Bristol. One, two, three, 1, 2, 3, 1, 2, 3, 1, 2. So this kind of combination. So, but I'm also interested in exploring the different representations that state-of-the-art machine learning techniques can learn from those rhythms. And I want to play with models that can be steered and customized and use them in my creative practice. So for this project then, I started doing a thorough review of all available kind of neural network architectures for encoding rhythms back then. And in this list, I show a few of them. There are a few other models, but most of them are based on the representations of Music VAE by Adam Roberts and Group VAE by John Gillick from the Google Magenta team. But by implementing and playing with these neural network architectures, I found 2 big issues. So the first issue is that all the systems were not designed to encode music in compound meter, not even triplets. So that pa, pa, pum, pa, ku, ka, kum, they are not able to encode that. So that's really bad, because that not only somehow affects the contemporary dance, contemporary genres that I wanted to play with, but also they cannot encode all the many African and Latin American rhythms that are in compound meter. So it's really was kind of, okay, we need to do something about this. But the second issue I found was about model complexity. So to be trained, most of these major neural networks required massive data sets and large processing power. So training usually takes a very long time and cannot be done at home. And this is because most of these systems were designed to learn one big model for many genres at once. And so you usually end up with a big model in which you have rock, jazz, reggaeton, classical music. And that can make sense for a big corporation which has to do something for the whole population. But if we're building something for an individual project or for one creative practitioner, perhaps something more limited in scope is better, because you want to work with some specific palette of sounds instead of having everything at once. But that's a typical approach in machine learning as a corporation, in which the more the merrier, no? The more data, the better, because you tend to somehow fix and make a solution for everything at once. So these 2 issues are very problematic because they introduce some biases, no? So there were certain groups of people, their musics and cultures. The first problem, the data structure, introduced biases towards particular genres and cultures because only certain rhythms, types, and musics can be encoded and modeled by the neural network. And this is in addition to all the other biases introduced also by the data used to train the models. But the second problem, model complexity, introduces biases towards particular types of users, because these neural network architectures require massive and very expensive data sets, only allowing some people or corporations to train these models, which hinders access to customization in a way. So it's very common that individual creative practitioners like us can't afford to train this very large system. So I decided and we decided here, because I'm going to talk for me and my co-authors here, to work on these problems and come up with a series of solutions. And the solutions were first to extend the data structure in order to accommodate and encode triplets and rhythms in compound meter. And second, to use a much simpler neural network architecture, more inclusive of people working in home environments by modifying the data flow and the connections of the model here. So we implemented this Rhythm BAE application, which is an application that uses the data structure I just mentioned and a variational autoencoder architecture, and that we, and when I say we, it's Louis McCallum, Esteban Maestre, Rebecca Fielding, and myself, published at the Journal of Creative Music Systems in 2022. So this application comes packaged as a Max for Live device so that musicians can easily integrate it into Ableton, which is a popular digital audio workstation, and also as a JavaScript application, such as the one that you can see on your right there. So the metaphor to play with this application, and we're going to listen to it in a couple of minutes, is that you, the performer, you are in control of a playback head in a multidimensional space, no? And two gestures are possible here with this playback head. So clicking retrieves and decodes a rhythm from the space, so tac, 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 tac. And also dragging interpolates between different rhythms within the space. So you can click, tuk, 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 and also you can drag, and you can create rhythm trajectories, let's say, in the space. There are also additional knobs, for example, for controlling threshold and noise, as you can see here, and that allows you to control the density of the patterns and the variability of the patterns, and so on and so on and so forth. And also we came up with the idea of creating a visualizer of a latent space, because when you learn something with machine learning for a computer, we are somehow blind. We don't know what the machine has inside. So we came up with the idea of, okay, can we show the different patterns learned by the computer? And we synchronized that visualization with the actual music beats. So I will show you that. You can think that kicks are red, snares and grits, and hi-hats are blue. So I'm playing. Okay, so that's a visualizer with RVA. So with a data structure able to encode these triplets, a much simpler neural network architecture and a latent space visualizer, and then I say I because that was only me, I started working to make music. So I spent several months working on collecting data from the rhythms I just mentioned, training models, improvising with the models, training, retraining, deleting points, adding new rhythms, and so on and so forth, until I got to a point in which I had a smooth model, also with some variability, so that it was somehow interesting across all the space. These are some of the examples that I was having for training. So I have 12 tips. Very simple rhythms. Then I was able to train this in the context of Ableton Live. The process of using RVA, the process of training ran for a couple of iterations, Then the visualization was generated. And then I was able to play with the visualization first on the context of Ableton Live, but later on. So the visualization now. Now I have a different representation, but instead of playing with a computer mouse, I'm also a person that likes to embody it. So I put also on top a touchpad interface to control how I was interacting with the system. This decision allowed me for a multi-physical mapping between the musical gesture and the sonic output. But on top of that, I decoded the output of the latent space to an external synthesizer for increased control in the sound design. Same system. my threes. So all in all, I ended up with a set of 9 tracks that I compiled on a full-length music album called Clastic Music. Clast is a term used in geology that refers to newly formed rocks and structures made from the accumulation of sedimentary materials from pre-existing rocks transported by a stream of water. So I thought, okay, that's somehow akin to machine learning, in the sense that in machine learning, we can use pre-existing data in order to create new structures. And in Clastic Music, I was using pre-existing drum patterns to create new rhythmic structures. And I was very happy to premiere this and perform with RVA Live at the 21st edition of Mutic. And this is a snippet of that show. Okay. I really hope that it's clear from that specific research project how I've been playing with this data-driven approach to create new things, and also an interaction-driven approach to create new sounds and new music with machine learning. And I have used this to support a sustained musical practice over time. On top of that, I've been also somehow interested in modeling sound directly. So I've been interested for the last couple of years actually in using machine learning to produce sound directly. So I've been somehow pretty much aware of what's going on since actually 2020 with Jukebox. During the pandemic, we started listening to very weird combinations of Frank Sinatra rapping on top of a NAS songs, very strange, you know, but I was pretty much aware of what has been going on. So then we have DGSP from the Google Magenta team, Rave in 2021, until last year there was released Stable Audio Open, which is a text prompt that generates directly sound using a diffusion mode. But what's interesting about this one is that it's trained on creative music with a Creative Commons license. So they are doing kind of a fair job, Stable Audio Open by Stability AI. But among these, the ones that actually are more interesting to me are this one, DGSP and Rave, basically because they can be trained with small-ish data sets, like not that much data, and also they can be controlled and steered in real time during performance. So those are the two elements that I wanted to play with. That is, after you curate and collect your data set to train a model, you can steer it depending on your interaction choices. So you have a data set of sounds, you feed it into the model, and then you have a model with which you can play with. However, playing with this model, it's pretty complex because you don't know how to play with a model, in the sense that it's like having a huge synthesizer, a new synthesizer, you load a new model, it's like you load a new patch, but there are no labels for all those knobs. So you don't know what's really going on. So you can start playing around your synth and you learn, okay, so this is related to a perceptual thing which makes sense. But then you load another patch and that the effect is different. So it's kind of very confusing. So I had a bunch of different questions. For example, how can we navigate this unlabeled high dimensional latent space? So how can I play with all these parameters in real time? So it was very confusing. How to perform real-time interaction with these latent models, how to provide this long-term coherence, because these models are pretty good, for example, are generating sound in the short time span. They make something that sounds like sound, but they are pretty bad at the overall narrative, you know? So if we're able to control and to provide this narrative back, we're somehow controlling the system towards a certain direction that we want to go for. And this long-term coherence is very important in linear media music. We want to make a whole narrative, you know? And this is still missing in all the state-of-the-art generative music systems so far. So Rebecca Figueroa and myself came up with this idea to play with these high-dimensional machine learning models of mapping our human performance space to the computer latent space using this interactive machine learning approach. So here on your left, we have our human performance space. We can sense our positions or our gestures in our space in the same way that Marcelo was somehow sensing the violinist. You can have any sort of measurements of positions or tracking, etc. And then we can map this performance space to the space of the machine, to this giant synthesizer with many parameters. And we can learn a mapping between these two spaces by using an interactive machine learning application. So for example, you can say, when I do this gesture, I want that configuration of the synthesizer. When I do this other one, I want that other different configuration. Then I learn a mapping, and you can do the two movements. And so you can have somehow a interpolation between these two sets of sound setting. So I started collecting a number of different data sets in order to train these RAVE models. And RAVE is interesting because it allows for the modeling of polyphonic signals, so complex signals. So I started to train on different sets of sounds, so acoustic harmonic sounds, so 32 hours of those, acoustic percussive sounds, electroharmonic sounds, electropercussive sounds, a data set collected by my friend Bruna Colasso, which is 4.5 hours of friends speaking poetry, also a data set of my edited music so that I know it by heart. I know exactly what's going on in the data set. Also another data set made by Bruna, which is 4 hours of ocean waves splashing on rocks in Mallorca in Spain. And finally, a subset of the sound archive of the Museum of Memory and Human Rights from Santiago in Chile. So I started making different models for all of those data sets. So I'm going to show you a couple of examples of myself playing with this model. So here I'm studying and performing the acoustic harmonic model. So the movements in the performance space, so the green square in the black canvas, are mapped to the AA model via the Wakinator application, which is the user interface you see on your right. So what's happening here is that I'm able to steer and perform a large generative model with an embedded interface. But you know me a bit. You know that I like to embody things. So playing around with a computer mouse, for me, it's kind of, I need something more. So I'm using the same approach here. So I'm exposing that computer mouse into my touchpad, and I'm playing this. This is in Morelia, Mexico, for the Visiones Sonoras Festival. I'm playing the RVAE, which is the rhythm model, on top of the model of voices. And I'm going to show you. I need to open this thing. Yes, just a brief snippet. This is more weird music. What's happening here is that I am mapping 2 degrees of freedom, by position of my hand in 2 degrees to 2, I think it's 16 degrees of freedom of the mole. Okay, so here in this other one, 8 degrees of freedom. So here I am with my friend, my sound artist friend de los Muertos in La Villette in Paris, and I'm playing with a different model in which I'm using a game track, which is a tethered device for controlling a golf thing, in which you have 6 degrees of freedom, and I'm mapping that now into a 16 degrees of freedom model. And this is what you can get here. Okay. And finally, in this example here, I'm playing at the SAT last October. This was a lecture performance. And here I'm using a head tracking machine learning model, which is based on the Google Media Pipe. And I'm mapping 1.4 thousand different points of my face into 8 knobs of this synthesizer. And this is part of the performance. It's funny that I have the same sweater. Okay, and I'm finishing. So, but when training these models, I experienced many unknowns, no? And I guess if you are using kind of machine learning for generating visuals or audio or all sorts of media, you are facing similar questions, you know? So for example, how much training data do we need? Small data set, but how small? How much variability do we need in data? Do we need somehow the similar thing over and over, or do we need to provide more variability? When to stop training? So for how long I'm going to be training? But then at inference or at performance time, other questions appear. For example, how can we explore a high-dimensional latent space? How to explore an unlabeled latent space? And how to explore something that changes for every single model. That's pretty confusing to me, perceptually, cognitively. And to finish, some of the insights I've acquired in my practice with these models are, first, that we can communicate intention through selecting the specific data set. By using our data, we can build a specific model with certain sonorities, certain characteristics, and we can play with that. The second one is that exploration generates knowledge. So by exploring and performing with a model many times, you start to learn the shape of the model, what kind of data you can decode from it. If you go to a certain zone, you kind of expect certain things, and so on and so on and so forth. It's a very this approach is somehow unsystematic because it's trial and error, but at least you are learning something about that specific model that you have loaded. The third one is that working with a well-known data set also generates insights. For example, if I play with my own music, I know exactly if the model is generating something new or not because I know it by heart. And finally, interactive machine learning interactions are useful when performing with real-time system because it enables us to introduce this long-term coherence and create narratives, you know. It allows us to control the overall narrative of the system. Rebecca and myself, we have recently published this in the Journal of New Music Research, in the same one that you showed in one of your slides. And I would say, just to finish, that these machine learning driven approaches for creating sound and music somehow allow us to interact and to create music in a different way. And ideally, having a new instrument will inspire us to make new music. So that's it.
Okay, so first, if you have, as I said, I mean, the initial conversation between you, and then we will move for questions from the general audience, okay?
Okay.
I have a question.
Good.
For example, how important for you, Marcelo, you think it's the sonic output of a new instrument for musical expression?
Good question.
Exactly. So how much relation is between the gesture and what you get back from the instrument?
It's interesting question because I'm not sure anybody was yesterday at McGill. At CIRMMT, there was the talk by Jeff Snyder. Mm-hmm. And Jeff was talking a lot about instruments and whatever. And one of the points he made is the instruments he builds, when he hears a piece, he doesn't see what's going on the piece. Ideally, he wants to recognize his instrument and to say, okay, oh, that was done with my instrument. Right? And we were talking today, actually, before coming here. And I think a lot is obviously the sound, but what in the sound? And I think a lot, in my case, that interests me is the articulation and the gesture that actually you hear through the sound. Right? It's not necessarily just the sound itself and how complex or how it evolves over time. It's the relationship of the result, the sound, and the gesture that produced the sound. That becomes less clear if you have a model that actually creates itself. Exactly. The model. But for me, I'm not the synthesis guy there. I'm again. It's really the gesture and you know, the intent and the interaction.
Maybe another question? What do you think, I mean, what is needed for kind of a new instrument to somehow get through?
What do you mean, get through?
But I mean, being popular,
karate instrument.
Being popular and being used beyond a turntable and beyond a CDJ, for example.
But you see, this is another very good one. What is the most successful? What is successful? Electronic instrument.
CDJ, like a digital turntable.
Yeah, maybe. What else?
Game Boy Color.
What?
Many Game Boy Colors were sold.
Yeah. The push, right? For instance, turntable, right? I mean, but we're talking thousands, maybe, right? We're not talking millions.
But I mean, right? CDs, these digital turntables are driving big chunk of popular music these days. No?
But what is the underlying thing that I think might be missing at some of these new developments? I think is the social context. Because when you buy the table or the push or whatever, you don't necessarily only play for yourself or in a concert for premiering your piece for your recital, right? Is the something that comes with is the group performance aspect. I think that sometimes is missing on new instruments. As we build something, it's very clever, it's very nice, lots of effort to play amazing music. But this context of sharing and performing and maybe drinking, not that this would happen, right? It's essential actually, I think, and sometimes we miss that because we are too much in a format, academic or elsewhere. But then what is a new instrument, and when the instrument stops being new? It's a problem I have with the NIME conference, right? New interface for music, right? So if it's always new, then you never develop something with the instrument because after a certain time it's not new anymore. Right? But I would say, very short answer, the social context, I think is, can we bring these instruments into social context?
Marcelo, before we go, do you have any comments?
No. I think it was one of the very interesting stuff about the Wakinator and the way you're doing, and it's a great point about not knowing the model and the model changing. So how do you interact with something you don't understand? But again, the notion of mapping, right? I mean, that you have to find something that associates. And this article, for instance, in this issue there's a lot of criticism on mapping. Oh, mapping is bad, but I don't see how you can do without some sort of correspondence. I mean, things don't happen. I mean, maybe we find ways to generate this correspondence without even thinking about generation.
I think mapping is crucial because you can explore things and you can find something interesting and then you save it. I usually use the word, I have a sound mark instead of bookmark, sound mark, a configuration. Then I dig a lot, I found another configuration. But then I want to create a mapping between those two. Because if you have some good anchors, you can go crazy to other zones of the space, you can very noisy, if you can go back to something that you can know. So you can play around, it's like with a rubber, you go crazy, go back. So you need those kind of anchor points. Having a good mapping allows you to traverse this space meaningfully, or smoothly, more than meaningfully. Yeah.
So, do we have something?
There were,
Nothing from the chat.
there are several.
Lynn is there.
We are open. Yes. Just for the recording, we need to. Sorry.
I just wanted you to tell us what the criticisms are of mapping.
It's not, well, I mean, there are several, there are several issues. Right? One is, if you think about physical models, so physical models for synthesis, right? I mean, you're simulating, how strings vibrate, how membranes move, et cetera, et cetera. So in this case, if you have a sensor that measures force, and you have an algorithm that actually, whose input is force, it's obvious the mapping is force to force, or et cetera, et cetera. So it becomes a bit less an issue of associating this with this because it's kind of there already. So this is one. So I remember I'm 2017, a big, it was Guy Wang's from Stanford's, keynote, and he said, "Oh, mapping, I never understood why this is important." I was like, "Oh, yeah." And I was there, and then there was a picture of both of us talking, and then someone put, "Oh, Marcelo teaching mapping," whatever. So, and it's obvious because if you use physical models, it is less important because it's there. But then there's also the issue of the model of mapping, this unidirectional model, whatever, that actually is a simplification. And we talk about this on the paper, right? But it's for the engineers here is the idea of linear time invariant systems, right? It is a simplification, but without simplifying problems to linear time invariant, you cannot use most of the DSP tools we use, right? So the problem is not the model, is extrapolating the model to making reality fit the model instead of model simplify reality. Right? So these are the two main ones, I would say.
Hi. In recent developments, we hear a lot about agents with AI. Like we hear of agents that can go off and code whole applications on their own. Is there any application of agents in the musical space?
Not that I'm aware of. No, I haven't seen agents. But that's a very interesting idea. For example, if you want to create kind of a non-linear music system in which you can have an agent somehow developing some sort of a musical structure or sound there, and you can play with another one, and then you can leave all of those running together, I would say that would be interesting. So instead of thinking about a linear composition, think about a process that you leave things running here and there.
Like I can imagine there's somebody, an agent creating the rhythm, another one maybe doing the melody, you know, and then they come together like a band almost. I don't know.
Hi, my question's for Gabriel. I'd love to know, how do you think about your relationship to the model while you're performing? And is it different from how you think of your relationship to other more traditional instruments which which have more control in your end?
Thank you. Excellent question. You know, since I know nothing about certain models at the beginning, when I load the model, it's kind of you are discovering something. So I start discovering kind of tiny portions of the space in which I feel, okay, this is a comfortable zone. This is something that there's value in that part. Then I play around with that portion of the space and I found something interesting. So I start sometimes, ideally, treasuring different portions of the model and actually treasuring the model globally. With some models, I mentioned to you the one with the water and the ocean waves, that model is beautiful, but it's mostly everything the same everywhere. So it's great if you want to generate that, but there is no much depth that it's hard for me to express. So finding a model in which I can create some sort of trajectory and narrative, it's somehow very nurturing in a way, because I know that it's unique to me. First, it's unique, your sound palette, and then how you traverse and how you explore this model in order to have something new, to create something new. And when I say new, it's that many of the sounds that we heard today were kind of bizarre-ish or kind of weird, but I think there is also value there because we know how to make an AO8 sound. No, we have instruments for doing that, so we don't need more instruments for doing exactly the same. But we have new instruments with which we can make new sounds. So that would be my take.
So in a sense, can you say that you are interpolating between local minima?
Yep, exactly.
I was just wondering, when you're doing research on these AI instruments, you showed a lot of videos of you playing on your own, but have you experimented at all with like two people playing different instruments that are, built on AI? And if you have, I would love to know what that was like, or is it kind of the thing where you're a step too far removed from the output to be able to collaborate in that sort of way?
No, I'd love to collaborate with more people. I play around a few times with my friend Bruna, but not in a concert setting. But I'd love to do that. I think there is lots of opportunities to play there. And I mean, my background as a musician is playing with more people. So that's how I learned how to play, by being in a band. So I love that, the communication. Playing alone in a way is great because you play with the machine, with your model, but there's something not missing really, but I like this idea of communication, that now it's your turn, now it's my turn. I love that. Yep.
Back to the social.
Yep, back to the social, exactly.
I was really interested in the motion capture study. I was wondering if you have plans to do anything further with that, like replicating it with other instruments, or if there are applications of that in AI, like reproducing those movements or creating new movements to trigger sound.
Yeah, that's yes for both. I mean, Alex here, right? I mean, you work with cello, organ. Yes, the project with organ. That was an interesting one. It was a student in performance, Dimas performance, looking at the different movements. So if you play the same piece, and so if I remember well, correct me. Yeah. Yeah. So if you look at the typical way of playing organ in the French school, whatever, it's very, only the fingers move, right? And then he was trying to use more pianistic tools to do the same thing, but and then compare, does the result change? And motion capture was really useful for really looking at a millimeter change here, millimeter change there, etc. So, but we did, I don't know how many, probably every instrument you can think of. The problem with mocap is what I was showing there is that, well, you have to put the markers, you have to do some measurements, etc. You have to calibrate the system, and then you have to look at the quality of the data, correct the data. And this is a lot of stuff. So it's not something you do like 10 people in an hour, in and out, right? So for practical applications, I think I can become useful, or different systems without markers, etc. So that you can use this in practice, not just in a lab and then measure the data and take as long as you need to. So I think that might be a breakthrough in the sense that finding systems that actually can do this for 100 music students and compare, or 10 at least.
I have a question for Gabriel, just to build up on Jake's question in terms of aesthetics. I want to more have a conversation about it. I understand that your models, you try to, especially you want to map out your interaction with the model, and you want models that are you're more familiar with, the data set that you're more familiar with. I was kind of introduced to this term of wilding AI and machine learning systems that are kind of wilding and are agents of chaos. In this kind of like incoming wave of AI aesthetics, how much of it do you think, especially maybe in your own practice, how much of it is kind of steerable, guided by you as the artist, and how much are you influenced by these sort of AI aesthetics?
That's totally true. The molds, I mean, the molds are chaotic. There are certain zones in the space in which there is chaos and noise. That's why I think it's very important, this idea of having a set of anchor points in which you know what's going on. So you can go into chaos, you can go into the wilderness, if you know that somewhere in the space you are in control, you know? It's like, I learned that also from you, Marcelo, for example, that you can be building kind of a new instrument, but you need a default state. So when you enter the space, okay, now you turn it on and you start sensing, but you need that going to your safe space. So I think that's really important. You can go anywhere in the space if you can go back and if you can play around with that. That's a pretty important point, Camille. Yeah. Thank you.
I have a question about also in the social line. Like, is there like ambition to bring this to the popular like side? Like, it's the question for both, and like if it's like intended to be like popularized too, how can it be like made of interest for like, I don't know, a sonidero or like a grupo jarocho or like just popular music?
Big question. You see, the issue is why it's not more known or popular, whatever. There's no intrinsic reason that we don't want to. And I think this goes back to a big cultural issue, why certain instruments are more popular than others. Any bassoonists, right? You see, it's really tight, the culture, and I think it's a lot to do with social. So if ever new ways of making things together happen, then definitely. Right? But as Gabriel was saying, certain instruments did become popular, and I don't see any reason why they have to be only using this kind of music. It's altogether market with. I mean, just look at the history. Sorry to. Go. But even big synthesizer. I mean, anybody, the Prophet 5, 1980 when? I don't remember, 3, right? How long did they produce it? Anybody knows? DX7, Yamaha. I mean, it's these kind of the landmarks, right? I mean, they are produced for 5 years, 3 years, the Minimoogs, but now they come back. And I think now we reach this stable moment where you can buy something that is still manufactured. But it's really a market with social, with a lot of things happening at the same time. Sorry.
I was thinking what you were asking that is that perhaps there's going to be a breakthrough at some point if there is a new way of interacting with the model. Within the next couple of years, I would say that there will be kind of interfaces for text to generate sound that will catch the attention of many people. And I believe that it's going to start by generating music for TikTok videos, for example, or any that sort of things. If that it's going to go into some more kind of a professional, creative side of things for actual musicians, I don't really know, yet. But I mean, I would expect that there will be a breakthrough in which there will be a couple of applications that will change how people in general generate some sort of sonic output. I would, instead of saying create music, generate some sort of sonic output. Yeah.
Can I do a follow-up? Sorry. It just, is there like intentions in the field to make it interesting to the?
I would say yeah.
Like I'm thinking of like, I don't know, like the Sackwood, like Czegledy was trying to make it like functional for the performer, no? Is there like intentions to make it like functional for the DJ, for the raver?
I don't know. But there are so many different things. For example, for DJs and those kind of things, I was thinking that, I mean, you could, first, all this AI-driven, for example, for stemming, for creating stems of music, it's perfect for DJing. For example, you can have a track and you can have different stems, and instead of just mixing two different tracks, you can mix by different instruments. That's a perfectly doable application, which is actually what DJs are actually doing with the filters, But here you can have totally separated stems of audio. So I think it's not just text to sound. There are many different ways of using machine learning for many different sound practices. Yeah. So we are already using them. Yeah. Also, for example, sound restoration and all those sort of things. That's these diffusion technologies are perfect for doing those sort of things. So we're going to have a lot of more machine learning applied to sound content within the next couple of years.
Question for both speakers. I was wondering if you could comment a bit on your thoughts vis-a-vis the longevity and preservation of these kinds of systems, particularly, Gabriel, these AI-driven model systems. I wonder what the long-term outlook is like for if we are still interested in using the model that you've nurtured now in 30 years, will there still be a way to run it? What are your thoughts on these issues?
Yep. I believe that if we don't rely on third-party APIs, we are safe because it's very likely that we can run our models, for a limited amount of time. If we rely on third-party APIs, services provided by any cloud provider, we are somehow doomed, because that's going to change soon. So I think it's good that we work with much smaller systems that we can run on our personal computers, than we can train ourselves, because we are more in control of the machine, the machinery.
But this is a good question. Thanks, Travis. For instance, we depend a lot on technologies, right, that we don't control. And so, new macOS, oops, your Mac's objects, bye-bye. So there is a question of, obsolescence of the technology itself. And that has always happened. So then the question is, can you overcome, as you were saying, right? Maybe if you control the algorithms, whatever you can do. And, but finding ways to bypass this. For instance, you have your favorite Stradivarius and the brakes. You won't find the same wood, right? You will not find exactly the same piece of wood. You will find a piece of wood that somehow will fix your problem. So can we have something like this on the electronics? You don't have the same component because whatever. Can we find something that simulates, et cetera, et cetera? But it's, again, the cultural thing. And I hope I'm not misquoting, but if I remember well, Robert Godin, right, from Godin Guitars, We were talking once about, and I think he said this, and I wish he had said, musicians want the latest iPhone and whatever, right? Or the latest computer to do this stuff, but they want the Gibson from the 50s. Why don't you get the new stuff? And again, the longevity, I think a lot has to do with expectations and etc. Right? So instruments that are super popular. I mean, how many synthesizer players do solos like in the 70s these days? I mean, maybe now again, but during the 80s, this was like, God forbid, right? Solo synthesizer only for the bass. But the guitar solo has never kind of disappeared the same way. The timbres that, depends on the style. But you know timbres, you listen to a DX7. Yeah. But you know, the DX7 sound, right? I mean, at a certain moment, and now it's like, oh, DX7 is so cool. Or the Hammond, or name it, right? So all these things that actually become very popular, then these modular synthesizers, that I think we never had so much access to modular, even in the heydays of Moog or Booklet, whatever. Right? So it's hard to tell longevity from disentangling all of this. Hopefully we get that.
Hi, my name is Alain Degnaud. I'm originator of Epic Grace University. I would like to know, I grew up in the 90s playing with big bands. I was wondering if the era of orchestra will come back, in your opinion.
Well, we had the digital orchestra at McGill. That actually was a 3-year project, but again, I wish, again, I don't see a reason why, I mean, it's the laptop orchestra idea, right? That actually, it's a great idea because, again, of the social part. I mean, people are committed to doing something, committed to finding solutions to whatever problem. And I wish, yes, I don't know how popular this will be.
But I think it's lovely because it's about community, it's about communication, it's about sharing things together through music. If that's a digital orchestra, fine. If that's a big band, also great, But it's the idea of being together, as in this room, in a way, and of sharing a common topic. I think there's value there, and I think we should foster those sorts of things instead of playing along with your model, like me, which was your question, actually. Yeah.
Can have a
Hi.
avatar.
This question's for Gabriel. I had the privilege of witnessing your performance at the SAT, and it's been festering since then how you evolve the motion capture to include your whole embodiment, because as performance was documented, you are so invested in evolving sounds through your body, and yet I don't have evidence of this. I see some like deep data sets producing texture, but not the gesture that you yourself create as you perform. And I wonder what the next stage is. Is that something that interests you in evolving, or is that?
Yeah, that's an excellent question, Dora. First, I have to say that I started my master's. My master with Marcelo was about touchless gestural control of a specific type of sound synthesis. So I've been all the time invested on controlling things in the air with my hands in 2 dimensions, 3 dimensions, dancing, all those sort of things. And so that interests me. And perhaps that's because of how I have this background with playing in a band in which you were on the stage and you have to play together for us. We have to have a good moment. So that's my idea. So, for example, in the show that you attended at La SAT, I'm just tracking my face, features from my face, but I'm doing weird gestures also. And that's just because I like to embody things. It's not tracking anything in the model. So I love to somehow having a full motion capture and being able to use kind of more complex body gestures and position in order to drive the system. Yeah, so that would be lovely. And think about, that's me, I'm a person that I don't have the dexterity and control, for example, that a dancer may have in order to drive a system.
You have plenty.
but just because of I love it. But I mean, there's people with actual control of their body. Yeah, so I see many possibilities for embodying these sort of things. And also that Rave is 2021, so I expect that soon we will have kind of newer architecture for doing nice sounds. Yeah.
We have a few more questions.
It's a question for both of you, kind of. Do you see the human voice or body physically anywhere in the future utilizing this, or do you see this as something the human should kind of react to?
So if integrating this into actual creative practice, or the voice and the, yeah, I totally see that from many different perspectives. First, we have somehow voice synthesis, so I can see totally. I mean, we've been listening to similar things lately in the media, you know, in which people have been cloning the voice of other artists. So I wouldn't like to go into that direction, but that's something that it's happening, and we're going to have more of that. So that's something that does not interest me personally, but it's something that it's up and coming. So we have to embrace it somehow. Yeah, I don't know if you.
Yeah, I guess that there's several applications of voice and gestures, etc. So there's no reason why, as long as you use, I mean, you can use the voice as something to be processed or as the main control. But the technology, I think, is there for so much. And there's lots, I remember papers in the 90s already, people using vocal cavity to control different things, and or probably much before with different methodologies, right? So yes, let's do it. Good.
I just want to make an announcement, because if you're talking real-time control with voice to visuals, tomorrow we're presenting a conference by Toronto artist David Rockaby in the fourth space. So the people will be able to experience his latest installation called Voice Scroll. So it's at 2 p.m. in fourth space, and the next day we're going. Everybody is invited to experience the piece in the visualization room from 10 to 3 p.m. tomorrow. No, Thursday. So conference at 2 in the fourth space tomorrow. Merci.
Cool.
So do we have any other question? Christian? Okay.
Gabriel, or maybe for both of you, I'm wondering about the corpus architecture and how that dictates mapping, basically. Like, can you think of new ways of organizing a corpus, basically, or to what degree does that dictate what's possible from the HCI perspective? Does that make sense, what I'm asking?
When you say corpus, you mean a data set, or?
Sure, yeah, like the latent space, I guess. It's like a three-dimensional space, I guess. Is that right? Like.
No, it's a multi-dimensional space. For example, I showed you a couple that were 16 dimensions. So it's easy for us to imagine sounds projecting this space in 3 dimensions.
Right.
No? Easy, like a cloud of sounds. If you add another dimension, it's like a cloud changing over time. But you can have 16 of those dimensions. So we cannot imagine those, but you can traverse this space using the computer. You can go into a certain direction and so on and so forth. So it's hard for us to imagine ways of interacting with that because we cannot visualize them. But when you train these models, you choose how many dimensions you want. You can say 2, but everything will be super dense, super packed. If you choose lots of dimensions, sounds will be more kind of spread out, but in a way it's harder to control because you will have more knobs of your synthesizer. So there is a trade-off, how many you need, how many you want. And then what each of those mean, we don't know. So perhaps one of the biggest and important things that will come soon, I would expect, this field of explainable AI, so explaining what's the feature that defines each one of those knobs. No? Because that's when we say the black box of AI is that exactly that. We don't know the label of that specific dimension. Actually, it's a mixture of features. But I mean, ideally, we would be able to put, I want to know what exactly this is doing, you know? And try to somehow find a correlation with something that we can understand. This is the timbre, frequency, resonance, or anything, something like that. Yeah.
I have a question. I want to ask, do you have any examples of interesting, like deliberate misuse of either systems, either motion capture or neural synthesis? No, a lot of the audio agent stuff, there's been interesting mismatches where you take one listening agent and match it to a different synthesis agent and get different odd outputs from that. But I don't know if there's anything that comes to mind for either motion capture or the neural synthesis stuff.
I don't know anything by heart now to tell you immediately, but I think misuse is basically at the core of the artistic practice, right? I mean, if you come and bring a manual and say, this is the way you use my instrument, it's guaranteed that you will get something else. And I think that is the interest, right, of you know, how people appropriate, get, you know, to use something without necessarily following a recipe for. But I don't know, mocap, what could you do? I mean, I guess you can really misuse in so many.
But I think, for example, in a research that we had together, we compared different kind of motion capture systems.
Yep.
And musically, I found that the most interesting one was the cheapest one, because there was more noise.
Yeah.
And instead of having a point in space which was perfectly kind of fixed there, like it was all the time moving. And that's something what you want in music. So you want a small variability within a certain, I mean, control variability, you know? And so the cheapest actually was somehow, I wouldn't call it better, but more dynamic.
More interesting. Right?
Dynamic, interesting, and so on and so forth. So it's not a misuse necessarily, but there's value on kind of a low technology, kind of low-fi technology. Value in the low-fi.
And I think this is a great point, because actually we tend to think that the most expensive or the most accurate or the most precise or, you know, whatever variable is the best, and actually it's not at all necessarily the case. And it's really a question of what tools. They are tools, actually. They are things you use to do something with. I mean, of course, they're more than tools, but I mean, I'm saying there's something the goal is not to have the system, is to use the system to do something, right? In your case, it was funny because the most accurate, we found something weird there. And actually, that was not so accurate as we thought, but because the floor was not leveled. So you look at the things, oh, it's a mistake. No, it's actually the floor. But it's useless for what he was doing, because in his performance, you wouldn't have a Vicon there with, I don't know.
Vicon was the motion capture system with the beacons, you know.
And I mean, it doesn't work on your setup. And the other one is so much more intuitive, but because the variables are not orthogonal, right? I mean, it's hard to separate. Yeah. But again, the tool has to be useful for not for the tool itself.
Gabriel, you talked about how in trying to figure out mappings and anchor points, there's a lot of trial and error. I was wondering if you could talk a little bit about kind of that creative process.
Yeah, at least my process is just trial and error, which is very unsystematic, I mentioned. So that's not something that I would push someone toward there. There should be a more kind of engineering approach in which you can have a machine which is actually offering you kind of a few recommendations. So this is an interesting thing. And so you can do that with reinforcement learning. So do you like it? Good. I'm going to find something along those lines. So that could be a more kind of programmatic approach of doing things. But that has to be somehow implemented. And we can do it together with the student if you're interested. I mean, we can plan something like that, you know? So instead of having this more kind of exploratory.
Sorry?
No? Which is... It's fine, it's fun, but there should be a different way of doing it.
question for you, Gabriel. And if you start the same model in 2 different points, or where is your starting point, and what is the effect of the starting point on your final result? Does it matter?
For the training?
Or for your performance, when you discover a model and you want to start interacting, you choose a point, I don't know how, and if you choose another point, will you get to different paths and find different minima or whatever?
I start collecting these sound marks. So I can start, for example, or I end up with 10 sound marks, and then I go in my head or in my score that I should go from the 1 to the second, and then to the third one, and then I can go back to second, and so on and so forth.
But that's a sampling. You choose 10. You could have chosen other 10.
Exactly. And these spaces are huge.
Right. And then what is the impact of the moment you chose that specific one? I guess if you chose another region, you might end up with something very different.
Totally. Yeah.
So it's a very abstract in a sense.
It's an abstract thing, yeah. So it would be great to somehow systematize the process of finding things.
Or just explore forever.
Okay, one last question, and then we close.
Sorry, you started talking, and now I have a bunch more questions. But just so I understand correctly, you showed us your corpus. It was like 100 and something hours of audio, and then you run that through the autoencoder. Then you have your latent space, and then you find kind of different configurations in that 16-dimensional space that you're going to define as your anchor points, I take it?
Yep.
Okay, and then I guess just with some feature decorrelation, you're kind of figuring out the continuous space and how you can come up with like sort of quasi-linear mapping?
In simpler terms, so you have your model, which is, think about the cloud of sounds in this room. So I walk there, and I choose, okay, do I like this sound here, this sound palette around? Okay, this is cool. So I save it. I place a bookmark, a sound mark there. Then I found something interesting in this point. And so then I create a trajectory between these two. I can play around, I don't know, other type of sound. Then I found something interesting where you are, and so I define a path between those two. So then I can play around with I can create these trajectories, and I can play around those. That's the overall approach. Yeah, the conceptual is pretty simple, in a way. Yeah.
Okay, so yes, Nina, you want to say a few words?
First of all, I really would like to thank you very much.
Thank you, Nina.
Because it was so interesting, and everybody was interested because we had all these comments. So it's not just my little comment here. And I also would like to thank very much that you so faithfully stayed here and talked, and we had a conversation. I'm always very pleased if we have a conversation instead of somebody just getting up and telling their own story. I don't like that. But I thank you very much, and I do hope that you will be able to come to future lasers in Montreal.
Thank you.
Thank you, Gabriel. Thank you, Marcelo. And thank you, everyone, for coming. I'm happy to see many of my students here and former students, too. So thank you for coming. Thank you.